Hello folks. Normally this is the point where I would say to you, be sure that you don't watch this because it's going to be long, boring, uninteresting. Be sure to unsubscribe from this stupid channel and give it a big thumbs down. And you can do all that, which I strongly recommend, but what I want to try to do in this episode is to address what I see as, a bit of a problem that is out there, particularly with the use of, what am I doing? Particularly with the use of my props I can't find. With the use of Tesla drive unit replacement board, OpenInverter board. This is an old V2 one that I've just replaced in the Panzer. So I have my drive unit out of the Panzer, and I thought we would make a video addressing some of these problems which unfortunately are resulting in inverter failures, and unfortunately I think for most of us they're going to be catastrophic failures that make the inverter unusable. So what I would guess, judging by the way things tend to work on PooTube and so on these days, it'll be probably the regular viewers of my channel that are seeing this. So that being the case, what I would like to ask is that if you know anyone that's using or planning to use Tesla OpenInverter, or indeed other control systems, whatever they may be, in their EV conversion project, that you perhaps send them a link to this video, which I hope will be educational without being overly technical, and will answer some questions hopefully as to why these failures occur, and show you the simple steps that you need to take to ensure that they do not affect you. So without further ado, let's get on with the boredom. No, Elon. No. Alrighty, so I'm going to make out a little bit of a plan here for how we're going to approach these things. So the first thing we're going to want to do is we're going to want to do the basic electrical checks. With a multimeter. Okay, so that's going to be our first thing that we're going to do once we get our drive unit ready for surgery. Second thing is we're going to want to do a 12-volt test on the logic board. Okay, so that's before we do any soldering on it. Third thing, which I actually can't show you here because I don't have one, but what we can do is do a 12-volt test on the DU. So that'll be with the original logic board in it. We can just apply 12-volt power and make sure that it powers up, that it doesn't present a dead short or something like that. Now, unfortunately, as I said, it's not something that I can actually demonstrate for you because I don't have an OEM logic board. So, moving on, number 4. What we're going to do is we're going to solder up the logic board, solder OI board, So that's the connectors and so forth. And then once we have that done, we're going to do a 12 volt test again. Okay, so number 5, we're going to install OI board into DU. Number 6, we're going to 12 volt test DU with, I might as well put it down here, with OI board. Okay, so that's going to be a basic 12 volt test. Number 7, we're going to do an encoder test. Once we've our encoder test done, the final thing that we're going to do is we're going to do a low voltage spin test. So, there we have 8 steps that we need to take in order to ensure that we give ourselves the best possible chance of getting our drive unit working with our OpenInverter board. Now, what I would like to note here straight away is that it's not until this one, step 8, that we actually need to apply any kind of, I'll just put in inverted commas HV because, you know, we're going to be running it at a low voltage. But at no point during any of this stuff here do we need to actually apply any kind of voltage to the high voltage terminals of our drive unit. In fact, doing so before doing these steps in this particular order is potentially going to open yourself up to problems. Do here that would start to give us some confidence on our inverter before we would even bother with this, because just to kind of help people to figure stuff out. So we're going to need a multimeter with a diode test. So let me get you folks in here for a minute. There we go. Alright, so I need a multimeter. I'm going to put it on diode test, okay? We'll just short circuit our probes to make sure it's working. Let me put a light on this for you. You might have some you probably won't be able to see this, but maybe you will. So we short them together, we get 0. Now, let's try bringing you around like this. Might just work out. So, on our inverter, we have our DC bus connections. So the first thing that I'm going to do is I'm going to look down here, and on these main connections there's a little stamped plus and a little stamped minus. So the first thing I'm going to do, I'm going to take my positive probe, put it on the plus, and I put my negative and stick it on the negative. Now, I want you to see how the multimeter reacts. So positive on, negative on. So, see what's happening here. We shorted out first, and now we've rapidly climbed and gone open circuit. So that's test number 1. So what that tells us is that there's no horrific short circuits on our DC bus. And the reason we saw the voltage increasing here was our capacitors, of which there's 3, 1, 2 and 3, have charged up to the little bit of voltage that our multimeter provides to us. Now, that's good. Next thing that we're going to do, we're going to take our meter, but we're going to connect it backwards to the main bus bar. So we're going to connect the negative to the positive to the negative, and I want you to observe what happens. And we settle down at just a little bit under 0.6 volts. Okay, now your mileage may vary depending on what type of inverter and so on that you have. But that's typically what you should see. What that tells us is that the pathways through the body diodes in our inverter is correct. I won't get into too much of the technical stuff. These are just simple tests that pretty much anyone can run before doing anything else. So if when we did either of those tests that we got something like that, you know, so we got a direct short circuit with 0 turning up there, that would be bad, and I would not advise going any further. If we got an basically open circuit here when we did either of those tests, that would be equally bad, but probably not as catastrophic, but you'd have to do some more investigation. So next test, you can see all this now because my camera work is not brilliant, but up around the back of the inverter, so in between say the rear casing and the motor, there's a series of 3 bus bars. One here just behind, you can see where my finger is, it might kind of help guide you there, and so on. So what we're going to do is we are going to take our multimeter negative, place it on the main bus bar negative, take our, wait, I'm going to just pull these leads out a little bit here just so you can see things a little bit easier. So multimeter negative, bus bar negative, multimeter positive, we'll pick one of these, I can get to this one easily here. Oops. And we see our voltage increasing, and it basically goes open, which is exactly what we want to see. Now I'm going to try and get, well actually I don't have to for the purposes of this video, I don't need to do all 3, but let's say that we do them, we do 1, 2 and 3 underneath here, we should pretty much get that same response. Now what we now want to do is take our negative probe, put it on the positive bus bar, take our positive probe and put it on one of our guys here, and we're seeing just under 0.3 volts. So that is good. What we now want to do is do that across all, wait for it, 3 of our bus bars, and we should see the same result there. Lastly, I'm going to swap our probes, take our positive probe, put it on our positive bus bar, negative probe, put it on our inverter phases, and we should pretty much get again what you see here. So doing that around all 3 of them should basically give us that result. Now if we had a bad transistor in here, then when we do these tests, typically what will occur is the meter will give you a short circuit response like that. So your meter may vary, and your voltages and so on that you get really may vary, but basically what we don't want to see during these tests are any dead shorts or open circuits. So that's it. just a few hopefully simple tests that you can run here in order to give yourself some confidence before getting into the recording. Okay, we are recording. All right. So folks, here we are. Large DU logic board V6. This is the one that Johannes kindly donated to me for our Panzer upgrades. So quite a few things different, as I've mentioned in the past, on these boards versus the prototype one that I've currently in the drive unit, not least of which is having the ESP32 onboard Wi-Fi module. So the first thing we're going to do here is just a little quick power up test, and so I'll just show you how to do that here. If we come down to this corner of the board here, we've got a connector called CON3, just like the Model 3. And on CON3, the terminal closest to the edge of the board is 12 volts positive, and the one furthest is 12 volts ground. So we're just going to go ahead here and connect up a 12 volt supply to this connector and just do a quick power up test. Again, this board from the OpenInverter shop will have program and parameter in the STM32, and the ESP32 module will be programmed as well. So we just turn on our 12 volt supply, and we should straight away see here that we have one red LED on solid and one red LED flashing 10 times per second. And if I have a quick look on my desktop PC here, we should see that, yeah, we've an open network there, starting with the capital letters ESP, and that's for our Wi-Fi here. And if we connect to that and just point a browser at 192.168.4.1, we get our parameters. Now, at this point, we'll have verified that the board powers up, and we have communication from Wi-Fi to the STM32. So at this stage now, this is the part where some folks can have problems as well. We come into the task of soldering on the connectors. So I'm going to try and give you some tips on this. I soldered quite a few of these myself, not recently, because again I handed over these boards to Johannes, so he's been dealing with them now for the last few years. But what we'll do is we'll show you a few tips. Hopefully will come back to me. So first thing we want to do is make sure we have our connector for the right fitting. Quite obvious, but there you go. So that sits on there like that. Now what I see a lot of people doing is they'll kind of come into this and they'll try to individually solder each one of these points. Now you can do that, but it's a very slow, very tedious, and very error prone way of doing this. So what we're going to do is my kind of usual go-to in these situations. We're going to start off with some flux, and we're going to put some flux not just here on these pads, but here on our two outsides as well. And I'm going to drop my connector on there. Just make sure that that flux goes all over these pads here. That's the critical bit. Now what I'm then going to do is, I do have a little, it's just a little magnifier. You can use a lot of different things, even just a little magnifying glass will do the same thing, because the only real thing that we need to do now is to ensure that our connection legs from the connector are sitting as centrally on the pads as we can reasonably hope to get them. So I'm going to use the little magnifier and just get my head in there. And see, I am a little bit over to me, so I'm just going to go a little bit that way. Just like that, no big deal. A little bit more. It was a little bit too gentle on it. Now I've gone a little bit too far, but that's okay, because one of the things the flux will do for you, there we go. One of the things the flux will do for you as well in this situation is it kind of acts as a glue and stops the thing from flying all around the place. And again, just for people that want to know, who haven't followed along at home, this is the flux that I use. The only disadvantage of it is it smells really bad, so don't breathe it in, as what was that guide on the Will It Blend used to say? Don't breathe it in, or don't breathe that. So anyway, I'm not using a very small bit. This is, just give it a clean here so you can see it. It's quite a large bit. I'd say it's about maybe 3 or 4 millimeter bit. Nothing spectacular. It's just a standard kind of a shovel bit. So what I'm going to do here is I'm going to put a little bit of tin on it. Now I won't do all of these. I'll just do one. I won't bore you totally to death. There we go. And it's that one tacked on that side. Told you it smells bad. Now what I'm going to do is I'm going to put some finger pressure on that until that solder goes off. And then I'm going to remelt on this side and keep the finger pressure on there. Wow, that is bad. Don't breathe that. So, the reason that we want to do that, okay, I'll show you on the one of these other connectors here. Reason that we want to do that, really, that these little pins here sit up a little bit higher than the base of the socket. So we actually want to press down, we want to press those pins down onto the board. So if you just place one of them on a flat surface and press on it, you'll see the pins flexing a little bit when you do that. So now, that's the easy part. We've just positioned the connector on there. So now we're going to come along to do the really hard part. And you'll notice I'm not using my head in here. I'm not using any magnification on my head or anything. The only little bit of magnification that I used was just this guy, just to check that I was lined up, and that's it. We're done with the magnification. So next thing I want to do, get some solder, and then we're just literally just going to start heating these things up. And I'm not even, you know, I'm not even paying that much attention. I'm just basically drawing solder. I'm just adding solder to the bit, and I'm just drawing it. And you'll see there's big blobs and everything in there. We're not worried about that for the minute. What we want to do is keep this moving. We want to keep heat in these connections. That's the critical thing. If you use a very small bit, the problem that you have with it is that it will not heat the joints sufficiently, or it takes too long to heat them more accurately. But by using again, I'm just drawing that solder, Don't be afraid if you need more flux in there. Get it in there. Flux is our friend here. There we go, our solder starts flowing again. It's kind of miraculous stuff, really. Again, get some heat in there. Again, I'm going to need some more flux. You see, always the right amount of flux, as Lewis would say. Again, I'm going to draw it back the other way now. With a bit of luck, if I get the solder amount quite right, there shouldn't be any blobs, but more than likely there'll be one or two, but we can process them to a degree by bringing those blobs out to the ends and then literally just cleaning them off from the tip of the soldering iron. And if that doesn't work for us, we can go with a little bit of solder wick. Again, I'm just running now that I've got them all tinned. I'm just running more heat into them. You can see I have a few blobs down this end here, so just flux it. Fluxing technologies. There we go, and all of a sudden the blobs start to disappear. I don't know, I try to get that message across to people, and yet you'll see boards and pads ripped off them and all this kind of thing. Where a bit of cheap flux from Ali will basically do wonders for your life. And take it from someone, like I said, that didn't understand that until fairly later in my career. I have a little bit of an excess here, which a career that I end up having it. It's probably a euphemism, to be fair. Now, of course, trying to find anything on my desk after I've been away for a while is always a struggle. Do you have that problem? If so, you need the sponsor of today's episode, Brains. Brains are the surefire way to not be stupid like me. So don't be like Damien. Visit the link in the description and get 10% off your packet of Brains today. Really? This is what I get for tidying up. Okay. So we're doing it the hard way. Alright, let's see how it ended up anyway. See if I've embarrassed myself on camera yet again. Oh, damn. I'm actually half good. Alright, so I do have a short as I suspected, only on 2 here, but everything else is pretty much spot on. Where'd my solder wick disappeared to? What have you done with it? You crazy conspiracy nuts. What have you done with my solder wick? It's disappeared. It's all gone. Ah, really? It's all gone, Damien, is it? Yeah, that's why it's sitting there staring at you. It's a conspiracy. They're out to get me. Must be a big oil conspiracy. Alright, let's see if we can just blop that up. Again, this is where a big bit is into its own. There we go. And now what we need to do is just draw a little bit of extra solder in here. Because we've just wicked that up, there'll be an insufficiency on those ones there. So we want to just add a little kid of solder back on there and make sure these ones are wetted down. So that's the idea, folks. I'm probably already super bored by now. Which is all part of my conspiracy plan. Yeah, and they're all wetted nicely. But those ones there, yeah, they're actually okay as well. Yeah, that's it. There we go. So there's that one on. I'll go ahead and do the rest. Now we'll come back then for the next part. All right. So we're back now with all of our connectors mounted on the board. And I'm just doing another power up test here, just to make sure that I'm still communicating Wi-Fi, still have my LEDs doing what they're supposed to do, and I'm not drawing any abnormal current from my 12 volt supply here to indicate maybe I had a short circuit or something else going on. So at this point now, we're getting very near to where we will be installing this board in the drive unit. Now, before we do that, it's just worth mentioning a few things here. So again, assuming that you've purchased from the OpenInverter shop, you're all programmed, you've done a power test, you've soldered on your connectors, and we're pretty sure from visually inspecting that everything is doing what it needs to do in terms of the solder here. But what we don't know is whether this is going to function when we install it in our drive unit. But there's a few things that we can be aware of and a few things that we can test along the way to kind of narrow down any potential problems that we might encounter. So the number one thing to keep in the back of your mind is that regardless of this particular board and any problems that it may have, the design works. The design has been proven to work. So it's not like you're going to have you know, some random error in the design of the board causing you a problem. The second thing is that the only things that are going to stop this from actually working are faulty drive unit, an assembly error from the PCB maker, so maybe one of these components not properly soldered on all the legs or something like that. Or number three is a problem with our soldering of the connector headers. So that helps to kind of narrow things down rather than, you know, trying to go off in completely different directions. Fault finding is 90% sitting down thinking about what's actually going on. So that's that part. So let's go take a look at the drive unit. All right. She is in all her glory, folks. The first V2 prototype. You might ask yourself what happened to the V1. Well, I'm not going to tell you that. You're going to have to look back at my old back catalogue for yourself, but suffice it to say, I'm an idiot. Oh, Elon Goo got me again. Okay, so I know I'm pretty much out of touch with all things Muskian these days, but someone want to tell me in simple language what likes me, what in the Sam Hill is he doing with the Zuck? Huh? Like I said, I don't know much about anything, but what's some weird stuff going on there. I'm up. I'm gonna start Just going to snap these connectors in. Okay, so the next part of the operation that we're going to do is our encoder test. Now, also want to point out that what we have here at the minute is we have 12 volts power applied to the inverter only. We do not have any high voltage or test voltages or contactors, fuses, batteries, heater elements, anything connected up. We don't need them. We're not at that stage yet. So what we're going to do here is we are going to first of all get into our web interface, which we have here. And in my parameters, what I'm going to do is I'm going to verify a few things first. So at the time of making this video, we're on 5.27 sine. And the parameters we're interested in here is encoder mode. It's parameter 11 here. And we want that to be on AB. Now I've seen a few situations where you'll kind of get folks that say, oh, the encoder didn't work, but don't worry, I fixed it because I just changed to single and it works fine now. Okay, don't do that, please. Stay on AB for me. And then we're going to go to parameter 13 and check that it's on 36 PPR. So those are the two that we want to check first of all. Right, so next of all, we want to come down here to our, I think it's in derating these days. Yeah, now we have one called UDC min, and we're going to set that to 0 temporarily. And then we are going to come down to contactor control. And this is this trip mode that I was telling you about before. You can ignore that now because we've no contactors hooked up anyway. I'm going to change UDC SW here to 0 and press enter. So what that has basically done is it has removed any of the high voltage lower limits from the inverter. We want to do that because in this case we want to put the drive unit into run mode. Now keep in mind we've no high voltage supplies on here, so it's not going to turn. We're in fact going to provide that turning force, as we'll see in a minute. So next thing that we're going to want to do, and my one is going to be a little bit different here because in my application with the Panzer, I am CAN controlling the inverter completely. So I'll be sending the control signals, the throttle signal, and all that via CAN. In your case, most likely you'll have a physical throttle pedal hooked up, you'll have switches, buttons, things like that to provide the various forward, reverse, start signals and so forth. Now, so what I'm going to do here is I'm going to basically via CAN, I won't show this because I don't want to confuse people. Via CAN, I'm going to provide a forward signal. And I'm going to provide a start signal. And what we should see then when we come back is that up mode is in run. So let's see if I can do that without screwing up too badly. We're back. So at this point, our drive unit is now showing up mode run. And we have a direction. That direction is reverse. It doesn't matter forward or reverse. We'll make no odds for this job here. So, all right. The next thing that we want to do is we want to have a look here. Where are you gone? Here it is, for speed. So we're looking for the speed parameter. And at the minute, that parameter is showing us 0 RPM, as we'd expect because we are not turning. Now, we're not going to apply power here to the motor to turn itself. We're going to provide some turning force for it, which I will now demonstrate to you, hopefully with some trick AI enhanced camera work. So what we're going to do is we're going to come to this speed parameter. I'm going to tick the L box here beside this, and then we can just go up here and click on plot. And if we hit start plot here, we'll see that we get a graph of speed, which is currently 0, as we would expect. So I'm just going to stop that plot there. We're going to get set up over at the drive unit and see what we can see. Gunpowder, treason, and plot. Okay, wasn't that fun? Now, we got ourselves a little graph here. So what you would have seen occur, hopefully, if my AI enhanced camera worked, is as I rotated the basically drive shafts, we will have seen the speed increase here on the graph, then come to a stop, and then I rotated the drive shafts backwards, and we'll have seen some speed here as well. But this is a particularly slow graph, so you're not going to see a nice curve on it. The reason I did a slow graph here is because I need to be kind of running backwards and forwards here, and I needed to catch this here on the screen for you. So if you plotted it faster, you would of course see more detail in the speed, but the point is still the same. So this is what we want to see. We want to see that we get a speed signal from our encoder when we rotate the motor with the correct encoder settings with no high voltage applied at all. Now, there's one other thing that we're going to want to check here, and that's when we go to our spot values here, I'm just going to hit refresh. And what we want to make sure is the last error here, and that's just saying pre-charge just because of we've no HV on, that's fine. The last error we want to make sure does not say anything to do with encoder. If we had incorrect encoder values, if we had incorrect encoder wiring, or if there was a problem on our logic board with the encoder circuit, then that is where it will show up for us. It'll either show up in that graph where instead of instead of this kind of making sense, where we have a nice, low 80, 40 RPM, that kind of thing, the graph goes crazy and tells we're at 16,635 RPM or something. Or we just get a flat line. If you get that at this point, you get a flat line, you get a crazy graph, you need to stop, take a breath, and trace down your encoder problems. Now, I'm not going to get into that because this would be just a bottomless pit of a 6-hour video. It's going to be almost impossible, I would say, to get folks to watch this anyway. So if we make it 6 hours, there'll be no one watching it. So encoder checks have now passed. So the next part, this is the fun part. This is where we are actually going to apply some test voltage, let's call it, and attempt to make the motor spin under its own power. Alrighty, so got my drive unit connected here with my control signals. So As I say, mine is going to be different. So I've only got 12 volt power and ground and a CAN wire that also has a brake signal, because I'm sending the brake signal into the drive unit as a hardware backup, as well as CAN. So I'm not using my drive unit for controlling contactors, but it's perfectly valid if you wish to do so. So here we have our high voltage bus bars, and on one of these here you'll see a little plus. So that's our positive one. So the positive one is the one furthest away from the control signal connector. Now, let's spin around over here and we'll show you how we're going to apply that power. So, what I have here is I have a 10 kilowatt electric cooker element, and I have, I think it's a 32 amp circuit breaker. Just got a crocodile clip because I use these for a lot of various testing. And then this will be my positive, so I'm going to clip this on here to the positive, and I've just got a negative coming from my power source. So that's on. So for my first power up, I want my circuit breaker off. And what this means is that any of our, let's call it testing voltage here, must pass through the heating element. So that means when we first connect this, the heating element will act as a kind of a crude pre-charge, so we can pre-charge our DC bus capacitors with our circuit breaker off. Now, once we have everything powered up and we're ready to run, I'll just close the circuit breaker. Now, if something abnormal occurs here and our drive unit tries to draw more current than the circuit breaker is going to allow, that's going to pop off. And our motor could be turning, not turning, jerking around, whatever. But the heating element always remains in circuit. So any energy that needs to come out of these bus bars here can pass through that heating element and back into our test voltage supply. That's the critical thing to keep in mind here, folks. So, circuit breaker off. All right, so I'm going to go ahead and start up the power supply now. We've got to take the mic off, so blah. Okay, power supply start up. Okay, so the next thing I'm going to do now is I'm going to run over to the computer and I'm going to check that we're seeing a reading of our DC voltage that's now applied to these bus bars. And in this case, for some reason, we are not seeing that. And that's because I have made a mistake. So, here is another very valuable reason. I literally made a mistake here with this. I've connected this backwards. But my heating element here is starting to get warm. And it is limiting the potentially damaging short circuit current. So now I can connect them the right way around. I'll jump back up to the computer and we will see. That was a genuine error, folks. But if I didn't have my heating element system here, there would have been a big bang. And indeed, I am now showing just over 42 volts on my DC bus. So there was a very valuable reason that you may want to do that. So, last part of the puzzle now that we have everything confirmed, the reading voltage. I'm going to close my circuit breaker. And I have now bypassed the heating element, but it is still there in the event of an emergency. So next thing I'm going to do, point you folks at the drive unit here. I'm going to send some CAN commands to simulate start, forward direction and some throttle input, and we should see those rather greasy drive shaft flanges start to turn, so stand by. Okay, so what I'm going to do is I'm going to place the microphone around the motor. It may pick up a load of electrical noise because I have the CAN off the inverter here, but the sound in there may be somewhat beneficial for folks to hear so that you'll know what it should sound like. Hopefully, assuming I don't make any more mistakes. Okay, so there we have it. That is forward direction. So what I'll do now is I'll go ahead, stop, and so I'll take the throttle signal off. We'll select reverse and just give it a little turn there as well. And that is then verifying our low voltage test. And we'll be good to get this guy buttoned up. And there we are, running in reverse. All right, so what we want to do now is we want to do a little bit of theory here as to what can be the cause of drive unit inverter failures when it seems as if we're doing everything that we can to not have that occur. So before we do that, we want to have a little bit of an idea as to what's in our drive unit. And this will apply to, basically anything from a Nissan Leaf, Tesla, whatever. What you basically end up with is you have a motor, which we'll call M. We have an inverter. And that inverter typically has 3 power wires going to the motor. Coming out of the motor, you have a position feedback signal. That goes around like this, goes back in to the inverter. And that, depending on the motor, will be an encoder. In the case of the Model S, Model X, SDU, LDU. And it can be a resolver in the case of the Model 3 stuff and others. So that's pretty much what we get. Now, into our inverter then from the outside world, we send control. So throttle signal, start signal, forward, reverse, all that kind of thing. We send those signals in and we apply some kind of battery. So we'll say the battery symbol. Some kind of a battery. And that is basically how, very simplified diagram, but nonetheless accurate, of how most electric vehicle drive systems work. And also, in this case, our Tesla drive units that we're having problems with. Now, so what let's focus in on the inverter. What's actually in here. Now, we're not going to get into electronics theory or practice or anything. What we're going to do is we're going to just give you, hopefully, a little bit of a better understanding of what this does. So our inverter is basically a converter. What it does is it takes, we're going to supply it with a particular voltage V, particular current I from our HV system, okay? Now, out of this, it's going to convert that to, we'll call it V2 and I2. And that is going to go into our electric motor. Don't need to worry about phases or magnets or no magnets or whatever sexy names they want to call them. That's the basic principle. It's going to take a voltage and a current in and create another voltage and a current out suitable to drive a motor. Typically, what we do when we're doing the low voltage testing part is we take, usually, I would kind of recommend something around 48 volts DC. And we apply this to our, just call it LDU for this sake. We can say LDU, SDU. So we're going to put that in, okay? Inverter. And we're going to apply control signal. In this case, a throttle signal or manual signal coming in from the web interface. And what we want is we want our inverter to give us a voltage and a current derived from this to make this motor turn. Now, and it'll happily do that, assuming that everything is doing what it needs to do. So everything here, so that our control signals are correct, the configuration, both in hardware and software of the logic board that's in here is correct, assuming that the position signal being received from the encoder or the resolver is correct, and that we have sufficient voltage and current being supplied to the input side of our inverter. Now, this is the one here that seems to trip people up. So why does it do that? That's the bit we're going to cover now. Okay, so we've established that our inverter converts a voltage and a current that we supply to it from our high voltage, or in this case a low voltage test battery, and converts that into another voltage and a current suitable for running a motor. Now, and we said that all things being equal, the motor spins, everyone's happy, and we all go driving cars. Now, there's many to slip between the cup and lip, as the old saying goes. And the first failure mechanism that I want to cover here is when everything is working fine. So we'll typically have a battery. We'll say, you know, this is some voltage, usually like between 40 to 50 volts. And we have our, I won't bother drawing different parts of it now, it's just a drive unit, so LDU, SDU. Got our control signals. We've our high voltage negative or high voltage positive terminal here. So we'll connect this up, and most people when they're doing this, and I'm not faulting anyone here, I'm not trying to come off as in any way superior, because I can assure you I've screwed up loads of times. Most people will put a fuse in the line of some sort, and our drive unit spins away, okay, because we've gotten lucky. We didn't have any wiring problems with our controls, our encoder works, our settings work. We didn't go mad changing settings in here, and everything works away happily. So that's great. So maybe it works a few times on the bench, and you know, everything's going very well. So you got your throttle signal coming in here, and maybe you have a few friends call and you want to show them this thing because it's really cool. So you turn it on and you give it a bit more throttle. And then you give it a bit more throttle. So obviously this is going to draw more current from our little test battery. Current I, voltage V. One thing to note at this point is that to spin the LDU, so the bigger of the two motors, takes something around 100 watts of power. So not kilowatts or megawatts or anything, just 100 watts. So about like what an old school 100-watt light bulb used to take. Doesn't take any more than that, assuming there's no mechanical reason for the drive unit not to rotate. Obviously, the faster that we want to spin it and so on, it's going to take more power. So power, as we know, what's power? It's voltage multiplied by current. Now our voltage is going to pretty much stay the same here. So in order to increase power, we need to increase current. And we'll probably get to a point that we're going to increase current to the point that this fuse here is going to fail, okay? And when the fuse fails, it's going to disconnect the battery from the drive unit, which is what it's supposed to do. And the drive unit's going to spin down and it's going to stop. And we're going to realize that the fuse failed. It's okay, we'll just go ahead and replace that and maybe recycle the 12-volt power and try and spin again. And when we try to spin again, it's not going to work. And we're going to get an error on our web interface. And it's going to be this: overcurrent. And we're going to be real confused here because that's weird. Everything was working perfectly fine. But this overcurrent error is now coming up every time. Then we'll get maybe a little bit more confused and we'll start changing settings and changing wiring and all this. But no matter what we do, this overcurrent error is going to persist and it's going to prevent the drive unit from turning. Now, the reason that this has occurred under this particular circumstance is not because there's any overcurrent. It's because one part of the inverter has actually failed, and those are the power transistors. So then we're going to go on the forum, and we're going to be really kind of confused, and you can't understand this, like, because normally we'd be running this drive unit at over 400 volts, right? And it's fine. We were only running 40 or 50 volts. And we had a little, I don't know, maybe a little like a 10 amp fuse in there. So, you know, how can this damage the inverter? Well, to understand that a little bit better, promise I'm not going to get into too much theory in this one. The simplest analogy that I can give you that causes this is to think about how an ignition coil works. In a petrol vehicle, or more correctly, a spark ignition engine. An ignition coil takes 12 volts DC from your car battery and alternator, multiplies that by a fairly big current, we call it I, and through some magic called electromagnetic induction, gives you a very big voltage but a tiny little current. And that gives you sparks that ignite your fuel, and off you go driving down the road. So, what's the analogy between an ignition coil and a blown drive unit? Well, see, the motor in our drive unit has lots of these things. It's a little symbol for you. That is a winding. And these things are wound around an iron core inside the motor. Now, this is very simplified. We don't want to confuse people any more than we need to. And when we're running our drive system, we're sending currents in this way, and we're also sending currents then back this way. We call that one I2. And that's all good, right? Because that's how the whole thing works. That's what makes the wheels turn. That's what gets us down the road. But when we put current into one of these pieces of wire wrapped around a steel core, we charge it. And a simple analogy that goes very well with this, and it's easy to remember because of the shape, is to think of a coil spring, like a suspension spring. Now, if we take that spring, we'll take I here, this current, as a force that pushes on that spring and compresses it. We take I2, that compresses the spring this way. So under normal operation, that spring is working back and forth as our electricity runs in and out through it. Now, if we've the spring compressed, so let's say I've that spring really tightly compressed here by a current going this way. And at that moment, I've just given my drive unit some throttle, and this fuse blows. That current stops instantly, stops dead. There's now nothing holding that spring compressed. So it's going to do this. It's going to shoot out like that. Like if you see them on put an impact gun on the top of a suspension strut and just let the top nut off and everything flies away. Now that's the mechanical version. The electrical version is that we get very big V, very high voltage rock and roll. And that's the principle we have here in our ignition coil that gives us spark and and lets us go down the road. Sadly, if we do this in an inverter and a drive unit, we get a massive voltage kick across the battery terminals. Our battery is no longer connected because the fuse has blown. So the voltage across these terminals for a very short space of time can go to ridiculous voltages. And the problem is that the transistors in the inverter don't like that. And if you're unlucky, under those circumstances, those transistors fail. Now you don't know this because there's no explosion, there's no bangs, pops, smoke or anything like that. Because this is really, it's a really big voltage, but for a really short time, microseconds, nanoseconds even. But it's killed at least one of the transistors in here. So when you replace the fuse, you come back and you attempt with your control signals to restart, you get overcurrent because the logic in here can no longer control the necessary transistors to send our voltages and currents into the motor part to make it spin. And the inverter is damaged, possibly beyond, not beyond repair, but I would say just given the design of some of these things, probably beyond what the repair of most people, myself included, can actually achieve. So that's failure mechanism number one. All right, so let's focus in on how to do this in such a way that if we blow a fuse, we generate this huge voltage, that we don't get a big spike that ultimately kills our inverter. So what I'm going to do is I'm going to draw another diagram, but I'm just going to focus on this part. I'm not even going to include the drive unit. So we've got a battery that we want to use to supply power to our drive unit. So what are we supposed to do? Is it going to be, oh, don't use a fuse then, but that's dangerous? And yeah, it is very. So of course we are going to use a fuse or a circuit breaker or whatever. So there's a fuse. And there's my negative terminal. So this is my positive, this is my negative. Now I'm going to show you a trick I've attempted to demonstrate multiple times, and I even accidentally demonstrated on a Model 3 video from myself. What we're going to do is we're going to connect something across that fuse. It's going to look, the electrical symbol for it is this. That is a resistance. The most practical one that I have found for these applications is typically an electric cooker oven element. We're going to connect this in parallel with the fuse. Now, we're going to be drawing current here, as we did before. And we'll go to the failure scenario, whereby the current that we're drawing exceeds the rating of the fuse, and that fuse just pops, bang, open circuit. And our voltage that we have across the inverter now is going to try to go to very high values and blow our inverter here. But as it does this, the battery is no longer disconnected. And there is now a pathway for current to flow backwards. We call this I reverse. It can come down here, can't go through the fuse because the fuse blew, but it can come down through the resistance, up through here, into the battery. And the battery soaks up that voltage. So the voltage tries to go high, but it gets pulled back down by the battery. So it no longer gets to that point whereby it can catastrophically zap your inverter. So you can safely test any motor, inverter, Tesla drive unit, non-Tesla drive unit, whatever, if you follow that simple principle. And I had a situation here when I was doing reverse engineering work on the Model 3 drive unit, whereby I didn't have a fuse here, but I had a circuit breaker, and this thing was going snap, crackle, and pop. But I had the resistance of the what's it called? Electric cooker element connected in parallel. So every time I popped this, the voltage across the drive unit would try to kick up, but got soaked up by the resistance and the battery. And no drive unit failure. Finally, oh my God, you'll be glad this is the last part of this. Let's look at the situation whereby we have our drive unit again. We have our drive unit and we have our battery. And this can be high voltage in a car, or it can be low voltage. Doesn't make any difference during testing. And typically then what we're going to have is we'll have our fuse, we'll have our main contactor, like so, on the positive side. We'll have a pre-charge contactor here with a pre-charge resistor. We'll have a negative side contactor here. So this is neg, pause, and PRC for pre-charge, okay? Now, whether you control these contactors from the drive unit or you control them with some other mechanism, VCU, BMS, whatever, we're not too worried about that at the minute. That's not really the point here. The point is, how can we, now that everything's running, we're spinning away, everything's working perfectly, okay? And maybe we're driving down the road. And for some reason, again, not important here, positive or negative, or indeed both contactors, just open. It can be accidental, it can be a BMS going mad, whatever you choose. Well, unfortunately, we've now got a spinning motor, which has now lots of these springs under compression, and we're going to let them go when our contactors open. So we're not having a fuse failure, we're popping the contactors open. So we're just going to disconnect the battery, we're going to take that impact gun, we're going to pop the nut off the top of that strut, the spring and all the bits are going to shoot out. That's going to cause the voltage to go very high, and that's going to cause the very same thing. We're going to get a transistor failure in our inverter, and the next time that we try to start the car, overcurrent. So I've seen around the forums and stuff people that kind of realize a little bit about this, and they come up with ideas like for doing things like putting a multimeter or something across here. Yeah, you can do all kinds of stuff like that, but to be honest, that's just not gonna have any effect on it. The simplest way to avoid that is to have whatever mechanism that is controlling your contactors. Now, within the drive unit, it has the ability to control contactors. Some people use it, some people don't. But there is a trip mode in the web interface parameter. And the choices are, from the top of my head, something like this: all off, pre-charge on, all on. Sorry, I should point out that the drive unit doesn't control the negative contactor, so that's kind of a poor choice. It can control the pre-charge and the main contactor. So, this one is bad. This one's good, and this one's good. So, come back to our analogy here. If we trip the drive unit, maybe, I don't know, we hit a pothole, and we turn off all of the contactors, bang, that's bad. But if we only dump the positive contactor and the pre-charge stays on, well, then the mechanism that we described here, whereby any voltage that attempts to rise here has somewhere to go, can go up through the pre-charging system back to the battery. Likewise, if we leave all of the contactors on, well, then it can just go through the mains and back to battery. And you can restart your car and drive happily down the road. This failure mechanism, again, can happen if we're in a car, can happen if we're in high RPM regime, low RPM, etc. So the short version is, the TLDR, as they like to say these days, too late for that, is if you dump the battery supply to a drive unit again, various ones of these are more susceptible. I can get into the why of that in another video if you wish, but it's not relevant to what we're trying to explain here now. You will end up with potential for damage to the inverter. So now we know why, hopefully. So there you have it, folks. I hope this has been somewhat helpful, somewhat educational, and may help to dispel some myths, rumors, hearsay about some of these problems, particularly with the Tesla drive units. I know some of you will have questions. As always, best place to answer those is on the OpenInverter forum. I'm not going to get into the theory of why the Teslas are so susceptible to this and other, let's say, less sexy stuff isn't. If you want me to, I can make another video about that at a future date, but nobody wants that, so I won't do it. Right. What I would usually say at this point is, make sure you dislike, unsubscribe, don't watch this garbage, go watch a funny cat video, that kind of thing. At this point, as I said at the intro, I would like to ask people that are viewing this, have viewed it, to, if you know of anyone that's going to use Tesla drive units in their conversion projects. It doesn't matter whether it's OpenInverter running them, or Elon is going to personally land a friggin' space capsule in your back garden and turn the drive shafts by hand. There's still valuable information here that I'd like to get across to folks and try to get this little bit of and knowledge stream working in the community. So if you do know of people even thinking about it, actively doing it, planning, whatever, send them a link to this, please. It's not. I don't give a toss about views or ratings or any of that. I just want to get that info out there so that people can test these drive units and get them up and running and enjoy their vehicles. Because as I said, I suspect that the folks that will be seeing this will be the regular viewers of my channel who probably know a lot of this stuff anyway, but it's the people that don't, that are very kind of fresh-faced, that I'd like to try to get some of that information across to them. So that's it. I hope it is some use to folks, and we will be getting back to our regularly scheduled Panzer programming fairly soon with our drive unit, and we have some good stuff coming for the Panzer. But I just thought, since I had the drive unit out, I was doing a logic board swap, that this would be a good time to make this video. So that's enough. You've listened to enough of this garbage. Thumbs down, unsubscribe, but do recommend it to your friends that are thinking about Tesla stuff. And until next time, happy can time outing. Time outing? Time out? Can time outing? Is that a word?